Black holes are one of the most mind-boggling aspects of space. For a start, they aren't actually objects. They are the result of the extreme warping of space-time. And because of this warping, some really weird stuff starts to go on around them that will change your perspective of the way the universe operates around you. Some of it is so strange that perhaps you wouldn't believe it was true, were it not for the solid math that backs up their existence and properties, and the increasing evidence that the math is correct through observations in our own universe. Hey everyone, I'm AK and let's begin our today's video of black holes. I hope by the end of this video to have earned your like and subscription. Black holes come in a variety of sizes. The smallest observed black hole is around 3.8 solar masses. On the other side of the scale, we find black holes that have been in existence since almost start of the universe. Black holes weighing billions of solar masses. These behemoths are not only massive but also huge. They would easily fit in the entire solar system within the diameter of their event horizon. Black holes being created today are the final stage in the life cycles of particularly massive stars. When such a star is born, it is essentially balancing the weight of two forces. The first is gravity, pushing its mass towards its center. Down in the depths of the star, hydrogen atoms are crushed against other hydrogen atoms with such force that they combine to form a denser element, which is helium. This new atomic structure actually needs less energy than it did when it was two individual separate hydrogen atoms. So the extra energy left over gets released. This released energy is the second force. It radiates back out from the center of the star as heat and light, counteracting the force of gravity pushing in. In this state, the star will remain relatively stable until such time as the reaction begins to stop as it runs out of its hydrogen fuel. If the star is massive enough, once the hydrogen begins to run low, the star will combine the newly formed helium into even denser materials like carbon, neon, and eventually oxygen and silicon. But then it begins fusing iron. The issue with iron is that it doesn't save any energy in its new form, so has no spare energy to release. It just sits in the core of the star, growing larger. With no energy pushing back against the gravity, very quickly the scale tips. The energy of this collapse is astounding, but the force is dependent on the original mass of the star. Like a hammer striking on an anvil, the mass of the star rushes down to meet the core with such force that the rebound of the blow is what we call a supernova. Matter and energy are blasted out across the universe from the crackback in one of the largest explosions possible, which produces elements even heavier than iron all the way up to uranium. And what is left of the star? Well, it depends. If the mass of the star and thus the force of the blow was too low, what remains is a neutron star, a small ball of matter at most around 25 kilometers in diameter, and yet is so densely packed with mass that it equals 1,000,000 Earths. But if the mass and thus force was big enough, physics as we know it breaks down and we are left with a black hole. When you see an image of a black hole, the black sphere you are looking at is not actually the black hole itself. Scientists theorize a black hole's true form is probably even smaller and denser than a neutron star. In fact, it is like infinitely small and infinitely dense, a singularity emitting forces that warp time and space itself. However, we don't know. And the reason we don't know is because of something called the event horizon. All objects with mass exert gravity. We have known this since the days of Newton. However, when Einstein came along in 1915 with his theory of general relativity, a contemporary of his called Carl Schwarzschild reasoned from it that there could exist objects that were so massive they could create enough gravity that light itself could not escape. And if even massless light photons couldn't get out, nothing could. When you look at a picture of a black hole, you are not seeing the black hole itself. You are seeing the event horizon around it. the demarcation line where gravity has become so powerful that light can no longer leave. There is nothing but darkness. Now its effect on space is one thing, but black holes also impact another aspect of the universe, which is time itself. According to Einstein, space and time are inseparably connected, and the mass warps space-time. With the singularity's infinite point of mass, it stretches space-time so much that the event horizon also marks the point where time stops. Within the event horizon, space and time basically cease to exist, a place where there is no where or when. This produces an interesting phenomenon to an outside observer watching matter fall into a black hole. From their perspective, as the matter approaches the black hole, it will slow down until just before the event horizon, where it will stop altogether. You won't ever see it cross the event horizon. There will be no satisfying absorption. Instead, the matter will gradually dim until you can't see it anymore. When first theorized, astronomers and physicists were uncertain if black holes were actually real. It was only 40 years later that the first evidence of a black hole was recorded. In 1964, using newly developed X-ray satellites, scientists noticed an object in the constellation Cygnus that seemed to be emitting a large number of X-rays. Strangely enough, though, scientists could not see the object itself. It surprised them because if it was a star, it ought to emit visible light as well as X-ray radiation. Scientists call this object Cygnus X1. In 1970, as telescopes advanced, they noticed that whatever Cygnus X1 was, it had formed a binary orbit with a star in its system, and this helped scientists calculate its mass. They discovered that this invisible object was 15 times more massive than the Sun. As the densest neutron star had an upper limit of 3 times the mass of the Sun, scientists realized that this was most likely the first ever discovered black hole. Since then, we have discovered many black holes. Supermassive ones seem to exist at the center of galaxies, and we have even managed to take photos of some dark bloods against a swirling ring of matter that surround and fall on their accretion disk. This is how black holes can still be detected through X-rays. While black holes can't emit visible electromagnetic radiation themselves, the X-rays that come from them actually originate from their accretion disks, where infalling matter gets heated to millions of degrees Celsius through intense friction. Black holes with no infalling matter are basically invisible, with no bright accretion disk to spot. Exploring black holes is still a developing field in physics, and there is still much to learn. From just what we have learned so far, you may wonder if a black hole could ever stop being a black hole, or will it grow forever until there is no matter or radiation left in the universe? It would seem so. However, in 1974, in his paper entitled Black Hole Explosions, physicist Stephen Hawking suggested that there actually was a way that energy and thus mass could leave a black hole. But to understand why, we have to get into some extremely weird theory. We need to examine some principles of quantum mechanics. But first, let me ask you a difficult question. What is nothing? Imagine for a second a patch of space with nothing inside of it. It has no atoms of space dust, not even radiation passing through it. As near as can be seen, nothing exists within it. And yet, is there really truly nothing here? Well, no. Something fundamental exists here, and we can tell that this is the case when a beam of light travels through it. If you are familiar with the properties of light, you will know that light is actually waves of electrical and magnetic charge that are constantly propagating each other forwards in a straight line. Let's take a look at the word wave. A wave in the sea is a propagation of energy moving through water. If you were to look at an individual particle of water, it's not really going anywhere except in a circle. And yet because it passes energy to the atoms next to it, energy travels the shore in a constant motion that goes all the way to the beach. Similarly, A sound wave moves by passing energy between air particles, with each particle only moving a tiny bit, becoming energized and then passing the energy to the next particle in line. But in vacuum of space, where there is nothing in it, where our photon of light is traveling in waves, have you ever stopped to wonder what exactly is waving? This hints at a fundamental something that exists even in nothing, a fabric that makes up all of reality itself. Quantum physicists call this something a quantum field. Quantum fields are tough to wrap your head around, but they are inescapably important when it comes to understanding the fate of a black hole. We will explore this in depth in the next part. If you liked the video, don't forget to hit the like button and subscribe to my channel for more interesting videos. Thanks for watching and see you in the next one.